Swayam Prabha. Digital India. Educated India.
So let's look at the program execution stuff. So far, what we saw is we were able to create an executable, change its references from various data sections and so on, resolve all the relocation. So everything is now nicely present in an executable in an execution format. Now, let's revisit the executable view of ELF. So we had ELF header, we had something called program header, which I skipped earlier, but we'll see that now. And then we had all these sections which were merged together to form segments. Okay. Now, program headers is essentially what is defining these segments. Okay. So segments essentially have the type, what is the offset within the file, what is the address at runtime, what is the size, flags, and so on. So for example, let's look at the same example we had earlier. If I actually compile this program, and actually there is a typo, there shouldn't be -c here, so it should just be gcc m32 sample.c. I'll fix that. And if I examine the program header, the section headers look like this and the program headers would look like this. Okay, so there are 9 program headers. Now, one thing which you can see is there is something called as entry point. Okay, this is the exact address where the first instruction of your program would be loaded. And remember, the first instruction of your program is not the first instruction of main. Okay, it is something else which we will see later in the slides, but I already disclosed that it corresponds to _start. Okay, so _start will be loaded at this address. So no matter, so if you actually take your Linux, and this is obviously Linux specific, okay, Windows may have a different thing. So this is as I was mentioning earlier, this is specified by the ABI, and ABI is a combination of particular processor and operating system. So every combination of processor and operating system may choose its own set of contracts, which they call as ABI. So each of them are free to specify it, but they will specify it and they will follow it consistently. Okay, so on Linux x86, this is the ABI that the program gets loaded at this virtual address. So that's what is encoded in the ELF, and linker would have assumed this, and all the function addresses will be relative to this. Okay, there is this type of segments. So PHDR is just the program header segment. The load is essentially the segment that will get loaded in memory. Okay, and you can see that there is a section to segment mapping, that which sections are actually forming a segment. There is flag, which is indicating what are the permissions when we load this thing. So for example, if you look at this first load segment, it has a read permission and it has an execute permission. It doesn't have a write permission. Okay, what it means, and this, if you actually see, will correspond to the text sections. Okay, what it means is when the virtual address mapping is done by the OS, it would only mark the pages containing the text section as read and executable. So if you actually try to write into a text segment, you would get a segment violation. Okay, similarly, this load segment has a read and write permission, so it has actually data. If you try to jump into this and start executing, you will get segment violation because you don't have execute permission in this. Okay, so virtual memory is also giving you these other benefits where you can manage what pages have what kind of permissions, and that can help you achieve some of the security things which otherwise would be very hard. Okay, and each of these segment also has what is the file size and what is the memory size. Okay, how much it takes on disk and how much it will actually take on memory. And if you remember, the reason this difference might come is because you have uninitialized variables which were 0, which were stored in BSS, which didn't occupy space in the object file, but they will occupy space in memory. Okay, any questions here?
Why are the virtual and physical address the same?
Because in this particular case, the physical systems with virtual memory, okay, you can use it even on machines which didn't have virtual memory. So the way it works is it allows you to say same things in context of Linux with x86, which has virtual memory enabled. The physical address location would matter. It would be same as virtual address because the actual physical address would be managed by MMU and page tables.
Okay.
So is the entry point address same for all programs? Like,
Yes,
so
it
like
is same.
how does it work with address space randomization? Like in Linux, we have
Which is
ASLR.
correct, which is what I was saying earlier, that with advanced things which are used for security like ASLR and so on, things would be different. But even in ASLR and so on, they typically will change the address space layout for stack segments and heap and so on, not necessarily the text segment. So ASLR will typically modify the address space layout on where stack starts, where heap starts, and so on, and where the shared libraries are loaded, not the
Oh,
text section.
okay, so for the text segment, it will be, we can assume it's constant. Okay, thank you.
Correct.
Thank you.
Because what those techniques are trying to do is if you give a fixed position where stack is always loaded, which was the case earlier, then you could easily start causing stack overflows and so on, because you know what pointer to construct to actually use to actually start putting some garbage data in it, or address. You can override the function addresses and so on, function return addresses. But with execute segments, you anyway don't have a write permission. And there are other contracts which make it very hard to relocate the text sections, because you'll have to defer that all to loader, which makes it harder. So the text segments will still be there with ASLR.
Okay, thank you.
Okay. We kind of saw some aspects of loader already, but what loader is doing is essentially whenever it got the executable, it kind of took it and executes it. So it will essentially copy the code segment, data segment from disk into memory, and then it would jump to the entry point. And the entry point is provided in ELF, which we just saw in the earlier slides. And once the loader runs, it will essentially create, the loader's job is to create the same virtual address space or the address space layout that the operating system is expecting. And here it would also do ASLR and so on. Okay. So entry point, this I kind of already talked, that it is actually a underscore start symbol, and linker will always link in this crt1.o, which actually contains the definition of these things, which is a C runtime. And this is what the pseudocode of underscore start looks like. This is the actual implementation, which I will not go into. Okay.